Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of game theory with engineering applications. We'll dive into key concepts like introducing design and meaning, semiotics brief overview. Let's get started. Slide 1. Introducing design. In this slide, we introduce the concept of design and its importance in game theory. Design refers to the structured process of planning and creating systems, products, or experiences to achieve specific goals. In the context of game theory, design focuses on developing the rules, strategies, and outcomes that guide player interactions and decision-making. Let's break down some key aspects of design as it applies to game theory. 1. Rules definition. This involves setting the basic framework of the system. In game theory, rules define what actions players can take and the conditions under which these actions are valid. For example, in a chess game, each piece has defined movements. 2. Objective clarity. Every game or system should have clear and understandable goals. This ensures that participants know what they are trying to achieve. For instance, in a traffic management simulation, the objective could be minimizing congestion and optimizing traffic flow. 3. Strategic interaction. Game theory emphasizes how the decisions of one player affect the outcomes of others. Well-designed systems account for these interactions to predict and analyze behavior. 4. Payoff structure. Payoffs represent the rewards or penalties players receive for their actions. In an engineering context, designing the right payoff structure helps model outcomes such as cost savings or system efficiency. 5. Fairness and balance. A well-designed system ensures fairness, where no participant has an overwhelming advantage. In a network security simulation, balanced design means that both defenders and attackers have fair opportunities to succeed. 6. Dynamic feedback. This refers to providing real-time responses to player actions. For example, in a supply chain simulation, adjusting delivery routes in response to demand reflects dynamic feedback. 7. Optimization focus. Design in game theory often involves optimizing outcomes. This means structuring the system so players seek the best possible decisions within given constraints. Example: consider a traffic management simulation. Design elements such as road layouts and traffic light timings directly influence how vehicles interact and optimize routes. Significance: effective design ensures that systems are fair, clear, and capable of delivering optimal outcomes, which is crucial for engineering applications like simulations and decision-making models. Slide 2. Design and meaning. In this slide, we explore how design connects to meaning and how the structure of a system influences user understanding and decisions. Design and meaning in game theory refers to the relationship between the system's structure and how users interpret their interactions. A well-designed system should not only function effectively but also communicate meaning clearly to users. Here are the core principles of meaningful design in game theory. 1. Intentionality. Every design element must have a clear and deliberate purpose. For example, designing emergency braking systems in autonomous vehicles ensures safety under critical conditions. 2. Interpretability. Users should be able to understand how the system operates. In a decision support system, clear data visualization helps users interpret complex information. 3. Consistency. Consistent outcomes enhance trust. If similar actions yield predictable results, users can better understand and navigate the system. 4. Player agency. This refers to allowing users to make meaningful choices. In an economic model, enabling decisions on resource allocation gives players control over outcomes. 5. Feedback loop. Systems should provide continuous responses to user inputs. For example, in a robotic control system, sensors provide feedback to adjust movement in real time. 6. Significance of choices. Each decision should have a meaningful impact on the outcome. In environmental modeling, choices regarding energy sources affect long-term sustainability. 7. Engagement. Engaging design keeps users involved. Interactive simulations that adapt to user decisions maintain interest and encourage exploration. Example: in a supply chain model, design decisions about logistics affect future delivery efficiency, connecting structure to long-term outcomes. Significance. Meaningful design enhances comprehension, engagement, and effective decision-making, which is vital in complex engineering systems. Slide 3. Semiotics. Brief overview. Semiotics is the study of signs and symbols and how they convey meaning. In game theory, semiotics helps us understand how information is communicated between participants and how this affects decisions. Let's discuss the key concepts of semiotics in game theory. 1. Signs and symbols. These represent actions, strategies, or outcomes. For instance, in a cybersecurity simulation, an alert symbol may represent a detected threat. 2. Encoding and decoding. Encoding refers to how information is sent, while decoding is how it is interpreted. In AI systems, this can represent the communication between machine inputs and outputs. 3. Contextual meaning. The meaning of signs depends on the context. For example, a high bid in an auction may signal value but could also indicate desperation depending on the situation. 4. Signals in games. Players use signals to convey information or mislead opponents. In strategic defense models, signals can represent readiness or vulnerability. 5. Information asymmetry. This occurs when different players have unequal knowledge. In an economic model, insiders may have better information, affecting market behavior. 6. Strategic messaging. Designing messages to influence others' decisions. In social engineering simulations, messages may be crafted to manipulate human behavior. 7. Perception management. Controlling how participants interpret information. This is crucial in autonomous systems where machines must interpret environmental data accurately. Example: in auction-based systems, the amount a player bids signals their valuation of the product. Significance. Semiotics is essential for modeling communication, misinformation, and interpretation in complex systems like AI and security. Slide 4. Differences, design versus semiotics in game theory. This slide focuses on the differences between design and semiotics in game theory. Let's explore these distinctions in detail. 1. Focus. Design centers on structuring systems and mechanics, while semiotics deals with how meaning is communicated. 2. Goal. Design aims to optimize performance, while semiotics focuses on clarifying or manipulating meaning. 3. Player interaction. Design defines how players interact through rules. Semiotics interprets how players understand these interactions. 4. Information flow. Design manages the action-response cycle, while semiotics examines how messages are transmitted and interpreted. 5. Complexity. Design is more concrete and rule-based, while semiotics deals with abstract meaning and interpretation. 6. Application. Design applies to mechanics like algorithms, while semiotics applies to areas such as strategic signaling and hidden information. 7. Example: designing reward systems in a game reflects design, while bluffing in poker reflects semiotics. 8. Outcome control. Design structures how players interact. Semiotics shapes how they interpret these interactions. Significance. Understanding the differences helps engineers create systems where both functional mechanics and clear communication are optimized for better outcomes.